Welcome to Microlecture 18 on constitutional isomers and units of unsaturation. Okay, so one of the things that you're going to be asked to do is to look at a set of molecules and determine if that set are constitutional isomers of one another. And so let's go ahead and look at the three compounds that are across the top here and kind of compare them to one another. You'll notice that if these compounds are, not constitutional isomers of one another, that means they're identical. They're going to have the exact same IUPAC name. So they'll have the same longest continuous carbon-carbon chain. And that's kind of the long way to solve the problem, to go through and name each of them. We wouldn't want to have to do that. A good shortcut is just to verify that the same number of carbons are present in all of them, and then kind of take a look and see, how many primary carbon atoms you have. And I'm seeing 3 primary carbon atoms in each of these cases. Once you've done that, it's pretty easy to see that these compounds are all identical. Okay, so these would not be constitutional isomers of one another. Constitutional isomers, they do have the same number of carbons, but they're going to be connected a different way. So they're going to have different IUPAC names. These two on the bottom, we can clearly see that there's 3 primary carbons here, but there's 4 primary carbons here. So again, a nice quick shortcut. And then if we just count carbons, we see that they both have 6 carbons. So same number of carbons and hydrogens and everything inside of the compound, just connected in a unique way with different IUPAC name would make these constitutional isomers. The topic of units or degrees of unsaturation is one that is just helpful to learn as a kind of a shortcut or a tool. So with this first compound, what we're seeing here is that by having a ring, one ring in the structure, we have 2 fewer hydrogen atoms than we would if we could have the maximal number of hydrogen atoms possible for all the carbons that are present. Right, so saturated system, by definition, would be a compound that has a maximal number of hydrogen atoms for the given number of carbon atoms. All right. So this particular compound is going to have 2 fewer hydrogen atoms because of this ring. And so it turns out that 1 ring equals 1 unit of unsaturation. And it has 1 degree of unsaturation because of that ring. Another feature of compounds that reduces the amount of saturation is multiple bonds. And so this second compound has 2 of them. It has a carbon-carbon double bond and a carbon-oxygen double bond. So 2 double bonds. And each one double bond is also going to reduce the number of hydrogens that can be on this molecule for the given number of carbons by 2. And so each one is considered 1 unit or 1 degree of unsaturation. Alright, and so this one has 2 degrees of unsaturation, 1 for each of the double bonds. And then the last one, the last example here is just kind of a combination of both of those rules. We have 1 ring and we have 3 double bonds. So 1 ring equals 1 unit of unsaturation and 3 double bonds, and each of those is a unit of unsaturation. So we've got 4 degrees or 4 units of unsaturation. This tool will come in handy. And the last example, that type of question that you might be asked is take a compound A and find the isomers of A. So we're looking for a compound that has the same number of carbons, oxygens, but connected in a unique way. It's a constitutional isomer. A lot of times the functional group is going to change, and a shortcut here is going to be counting units of unsaturation. So the first thing I would do is count carbons and see that compound A has 6 carbons, and it's going to have 1 degree of unsaturation in any constitutional isomer that it could have, right? So if the compound below has 6 carbons, also 1 oxygen, and 1 degree of unsaturation, then it's a constitutional isomer of A. And so pause the video, go through and see if you can figure out which ones are indeed constitutional isomers. Alright, and so I'm seeing 6 carbons, 1 oxygen, and 1 degree of unsaturation. I'm seeing 6 carbons, 1 oxygen, and because of the ring, 1 degree of unsaturation. Here I'm seeing 6 carbons, 1 oxygen, and I'm seeing 1 degree of unsaturation because of the double bond. The 4-member ring structure is interesting. I'm seeing 1, 2, 3, 4, 5, 6, 7 carbons. Okay, 1 oxygen and 1 degree of unsaturation. The next one, 1, 2, 3, 4, 5, 6 carbons, 1 oxygen, and 1 degree of unsaturation. And then the last one, 1, 2, 3, 4, 5, 6 carbons, 1 oxygen, 2 degrees of unsaturation. And so immediately I can eliminate this as an option because it's got too many carbons, and this as an option because it has too many units of unsaturation. The rest would be constitutional isomers. Another great question that I could ask, and there are many possible answers for this type of question, is I would give you a structure and say provide an isomeric compound. It means provide a constitutional isomer. And so I'm looking for you to come up with a structure that has the same number of carbons, same number of non-carbon, non-hydrogen, so any heteroatom, in this case oxygen. And so more specifically, I'm looking for 3 carbons, 1 oxygen, and 1 degree of unsaturation. So there's, like I said, lots of different answers that you could come up with here. Pause the video, see how many you can come up with. So here I have a ketone instead of an alcohol, 3 carbons, 1 oxygen, and 1 unit of unsaturation. And I could also come up with an ether compound. And this one has, again, 3 carbons, 1 oxygen, and 1 degree of unsaturation.